Today I'm going to discuss the power rule for differentiation. When we are doing derivatives, we need to choose between one of our definitions. There's a definition where one variable approaches the other, one point approaches the other, or by substituting in x plus h where we have a difference, we can have the definition where the distance between the 2 points goes to 0. We're going to do this both ways today, and they use slightly different techniques. We'll do it both ways so that you can see that sometimes one may be more appropriate than the other. We'll start off with the 2 points approaching each other, and our function is going to be x raised to the n, where n is some integer. And we combine those together, and when I substitute in my function, I get derivative of x to the n is going to be limit as x naught goes to x of x naught to the n minus x to the n over x naught minus x. And I have this difference of powers. And we're familiar with some difference of powers. We know that difference of squares looks like this, and difference of cubes looks like this. And it looks like there might be a pattern there. If I set the exponent to 1, that looks like it's a reasonable part of the pattern, and if I set the exponent to 4, it looks like it might be this. I'm going to suggest you pause the video right now, try this out, and see if it actually works. If you checked, or even if you didn't, we'll see that it did, and we can look at what a more generalized form would be. And so we look at this and we notice that the second component of our product is going to involve powers that are 1 less than we had in the original expression, and they start with all powers of A and then slowly switch over to be all powers of B. So it'll look like this. And we want to test this out, make sure our theory works, so we're going to distribute the a minus b into 2 terms. And if we look at this and actually multiply these out, we see that everything except the first term in the first row and the last term in the second row are going to end up canceling each other out, leaving us with a to the n minus b to the n. Writing these in terms of ellipses is a little bit long, so we'll rewrite this long expression using summation notation, where it's just the sum of all the terms, and we start with a being equal to the power of a being equal to n minus 1, and b to the power of 0, and then as it switches across, it ends up being a to the power 0 and b to the n minus 1. We're going to take this and use this to substitute in for our expression above. So our x naught to the n minus x to the n is now going to look like this x naught minus x times the sum. And we are very lucky here that we notice that I have my x naught minus x cancels out with the x naught minus x in the denominator, and that eliminates our indeterminate form. So because the indeterminate part of the expression is gone, we can just now substitute in x for x naught, which gives us this sum. And we notice that since now the 2 bases are equal, we can add the exponents together, which cancels out the i's, and I get sum from I is equal to 0 to n minus 1 of x to the n minus 1. If we make sure to count that 0, the total number of times this is being added up is n times, and because I doesn't appear, we don't need to do anything special. We just add this to itself n times, and so we get our final expression is going to be n times x to the n minus 1. And this is in fact our power rule for derivatives. Let's try it the other way. So we're going to go back, look at it. We're going to use the difference going to 0 this time. Once again, our function is going to be x to the n. And we notice when we look at our limit expression this time, we now have this binomial raised to a power. And that brings us back to the general form of a binomial raised to a power means we need to use binomial expansion, which is this formula, as we remember from Algebra 2. It's a little bit ugly. Some of you prefer to use Pascal's triangle, and if we look at this first diagonal row of Pascal's triangle, we will notice that it also matches the powers of our binomials. We're going to keep this in mind so that we'll see the pattern when we look for it later. But for now, we're just going to use that kind of ugly formula and see if we can break out some parts of it. So we'll do this. We'll look at just the binomial term raised to the power n and write out that expression. And I want to figure out what the first term is when k is equal to 0. If I look at the factorial parts in the fraction, n factorial is going to be divided by n factorial, cancels out and just gives me 1. And the powers are just going to be x to the n and h to the 0, which is going to be x to the n. So that's fairly simple. I'm going to do this again for the second term when k is equal to 1. So notice that the sum has now changed from being k equals 0 because I pulled out the first term. It's now starting at k equals 1. We're going to do this again and pull out the next term and then have a sum starting at k equals 2. When k equals 1, I get n factorial over n minus 1 factorial, and all the factorial terms cancel out except for n, and the powers that I get are going to be x to the n minus 1 times h to the 1 power. So my second term is going to look like n times x to the n minus 1 times h, and now I'm going to have the sum starting at k equals 2. So we still have the same sum. We've just pulled out the first two terms separately and then leave the sum for the rest. And this is going to be just that x plus h raised to the n binomial, and we're going to substitute this mess into the limit and get this expression. This looks horrible, but there's already some things we see that we can simplify out. First one is that my x to the n cancels with the x to the n from the definition for the limit. And so that simplifies something a little bit. I can also separate this into two separate fractions now. And if I look at the first one, I get h over h, which is what made that indeterminate. Those are going to cancel out. In the second fraction, I have h in the denominator and an h to the k power in the numerator. When I simplify that, that is just going to give me h to the power of k minus 1. And so when we do this, all of a sudden I have once again eliminated my denominator, which would make these indeterminate, and I can now find the limit by just plugging in h equals 0. That first term has no h, so it's going to stay the same. It's completely unaffected by the limit. And the second one has 1h where we substitute in. So I get 0 to the power of k minus 1, which is undefined when k is equal to 1, but because our sum starts at 2, all of these terms are going to be multiplied by 0, and they cancel out. And this once again leaves us with exactly the same result for the power rule for derivatives. So this is our power rule for derivatives. Whenever I have x raised to some integer power, I can find the derivative by multiplying x by that power and then lowering the power by 1. So the derivative of x cubed would be 3x squared. The derivative of x to the 7th power would be 7x to the 6th power, and so on. This is going to be one of our easiest, most basic rules that we use. This is, for some people, the only thing they remember about derivatives, but we're going to look at a bunch of other rules. But this is going to be one of our building blocks that we can put together with other rules.